Today, we're diving deep beneath the Earth's surface to unravel one of nature's most dramatic and mysterious processes, magma chamber mobilization. You might think of magma chambers as these slow, ponderous giants, taking eons to stir. But what if I told you that sometimes their awakening can be surprisingly quick, yet intensely constrained? It's a dynamic interplay of speed and immense pressure that scientists are constantly trying to understand. And trust me, it's far more fascinating than you can imagine. So let's start by picturing a magma chamber. It's not just a big underground lake of molten rock, as many might imagine. Instead, it's often a complex network of interconnected pockets, dikes, and sills, filled with a mushy mix of crystals and liquid magma, kind of like a partially melted slushie. For a volcano to erupt, this magma needs to move, to mobilize, and ascend towards the surface. The conventional wisdom used to be that this mobilization was an incredibly slow process, taking thousands of years, building up gradually. But recent research, especially over the last few decades, has started to paint a much more dynamic picture. Scientists are now finding evidence that magma can mobilize and move through the crust much faster than previously thought, sometimes within decades, years, or even months before an eruption. This realization has profound implications, especially for our ability to predict volcanic activity. Imagine the difference between having thousands of years versus mere months to prepare for a major volcanic event. This quick mobilization isn't just about the magma heating up. It's about complex physical and chemical changes happening within the chamber itself. One of the key drivers for this rapid mobilization is the introduction of new, hotter magma from deeper within the Earth. Think of it like injecting a fresh, hot batch of cookie dough into a semi-frozen one. This new magma can instantly increase the temperature of the existing chamber, making the resident magma less viscous, more fluid, and easier to move. It can also introduce new volatile gases like water vapor and carbon dioxide, which dissolve into the magma. As these gases come out of solution, much like opening a can of soda, they create bubbles, increasing pressure within the chamber. This process, known as volatile exsolution, is a powerful engine for driving magma upwards. Another critical factor is crystal content. Remember that magma slushie I mentioned? If the amount of solid crystals in the magma decreases even slightly, the whole mixture can become much more fluid very quickly. This can happen due to heating or by mixing with a more liquid, crystal-poor magma. It's like turning a thick paste into a runny sauce. Once the magma crosses a certain threshold of crystallinity, often around 50% crystals, it can transform from a solid-like, immobile body into a flowing liquid very rapidly. But here's the catch, and it's a huge one. Despite this potential for quick mobilization, magma chambers are often held under immense pressure by the surrounding rock. The crust above and around these chambers is incredibly strong and acts like a powerful lid. So even if the magma inside is actively mobilizing and building pressure, it still needs to overcome this colossal resistance to move upwards and erupt. This is where the concept of being held under pressure becomes so vital. Think about trying to squeeze a very thick fluid through a tiny straw. Even if you apply a lot of force, the resistance from the straw itself and the viscosity of the fluid will limit how fast it moves. Similarly, magma often has to find or create pathways through solid rock, which is an energy-intensive process. It moves through cracks and fractures, sometimes creating its own by hydraulic fracturing, literally pushing the rock apart with its immense internal pressure. The crustal stress field plays a massive role here. Tectonic forces, the movement of Earth's plates, create zones of compression and tension within the crust. Magma will preferentially move through areas of tension, where the rock is already being pulled apart, making it easier for new cracks to form or existing ones to open. This means that a magma chamber might be fully mobilized, pressurized, and ready to go, but if it's located in a region under strong compression, it might stay locked for much longer. This interplay between rapid internal mobilization and external geological resistance is what makes understanding volcanoes so complex and challenging. Geologists use a variety of techniques to study these processes, including seismic monitoring to detect magma movement and fracturing rock, satellite imagery to observe ground deformation, and geochemical analysis of erupted materials to understand magma composition and volatile content. By studying ancient volcanic rocks, they can even reconstruct the history of how magma chambers evolved and erupted in the past. The implications of this research are immense for hazard assessment. If we can better understand the signs of rapid magma mobilization, we might be able to improve our short-term predictions of volcanic eruptions. It's not just about knowing that there's magma there, but understanding how quickly it's changing, how much pressure is building, and what the surrounding rock structure looks like. This knowledge helps us better interpret seismic swarms, gas emissions, and ground uplift signals that often precede eruptions. So, while magma chamber mobilization can indeed be surprisingly quick, often within timescales relevant to human lifespans, it's constantly battling against the overwhelming power of the Earth's crust. It's a dynamic dance between internal forces and external constraints, a battle of fire and stone happening miles beneath our feet. And understanding this intricate balance is key to unlocking the mysteries of our planet's most powerful geological events. What an incredible journey we've taken today, from the slushy depths of magma chambers to the immense pressures of the Earth's crust. I hope you've learned something new and fascinating about the hidden world beneath us. If you enjoyed this deep dive into volcanology, please give this video a thumbs up, share it with your friends, and don't forget to hit that subscribe button and notification bell so you do not miss our next adventure. Thanks for watching, and I'll see you in the next video.